In this video lesson, we're going to learn about geometric series. A geometric series is the sum of the terms of a geometric sequence. An example of a geometric sequence might be the sequence that starts at 1 and triples each time. So those terms would be 1, 3, 9, 27. And so the corresponding series would be 1 plus 3 plus 9 plus 27 plus, and so on. In our discussion of arithmetic series, we established the distinction between the sum of a finite arithmetic series, which we determined we could actually calculate, and the sum of an infinite arithmetic series, which we established that we couldn't calculate because the sum diverges. We're going to look at a finite geometric series now and an infinite geometric series and kind of go through the same process to develop an equation here. Let's start by looking at a finite geometric series. So here I've started off with a generalized sum of the terms of a geometric sequence, starting with the first term u1, and then each subsequent term multiplying by the common ratio until I get up to the nth term. So if you look actually over here, this is just our general term for the nth term of a geometric sequence. So I'm going from term 1 up to term n and finding that sum. Now, to go about developing this general formula for a geometric series, I'm actually going to take everything and multiply it by r. So on my left-hand side, I have the sum of the first n terms just times r. And on the right-hand side, each of the terms in this sum is going to be multiplied by r. It's actually going to increase the exponent on r by 1 for each of these terms. So these first three terms went from being u1 to u1 times r. So the exponent on r there went from being a 0 to being 1. The next term, it went from being an r to an r squared, and the term after went from being an r squared to an r cubed. And as I keep going down the line, we're going to see the exponent increases by 1 here as well. N minus 2 is going to increase to n minus 1, and in this last term, n minus 1 is going to increase to n. Now I can work towards simplifying this because there's actually a lot of commonality between this section and this section. So my second line, section I've underlined in purple, and my first line of this development, section I've underlined in purple, are actually identical. And in fact, my second line, the underlined portion, is almost identical to the first section, except it's missing the first term. What that means is I could actually take my first line and rearrange it, and basically say that the sum of all of those terms is the sum of all of the n terms, except for the first term. And then the easiest way I can generalize that is by saying that that is Sn, the sum of the first n terms, minus the first term. So I've condensed everything in that purple section to be written in a much more simple fashion. Nothing else of this development is going to change on this step, but you can see that I've now condensed everything to the point where I don't have that repeating section in the sum where I didn't write it because it could have gone on forever. I was able to actually make it much more concise. Now I can start to take this development and sort things based on what's similar. I'm going to move all the Sn terms to the left-hand side. I'm going to leave all the U1 terms on the right-hand side because that's going to allow me to do some common factoring. On the left, I can common factor out the sum of the first n terms. On the right, I can common factor out the first term. And we have to remember my goal here was actually to find a generalized term for S sub n, the sum of the first n terms. So I do want to actually get it by itself. I'm going to divide both sides by r minus 1, u1 r to the n minus 1 over r minus 1. And so that becomes my generalized formula for the sum of the terms in a geometric series. So using this newly developed formula, I can very easily find the sum of the first 7 terms of a given sequence. So this is a geometric sequence that starts at 2 and has a common ratio of 2. It's doubling each time. And so the sum of the first 7 terms is going to be 2 times 2 to the 7 minus 1, all divided by 2 minus 1. And so as I go in and simplify this, I can very easily find the sum is 2 to the 8 minus 2. So that is just 256 minus 2, or 254. And so there I was able to very quickly find the sum without calculating all of the terms, and it's much more efficient to find the sum of a geometric series this way. So now let's talk about if we can actually find the sum of an infinite geometric series. So when we looked at an infinite arithmetic series, what we realized is if you're starting with an initial term and putting a common difference on it each time, ultimately it's going to end up diverging. if your common difference was positive, we're going to get increasingly large positive numbers. If your common difference is negative, your sequence is going to keep getting larger negative numbers. But it's never going to zero in on a specific sum if it goes on forever. And so geometric series, we'll investigate a few here and see if the same sort of problem arises. So let's actually start with a sequence that begins with 1 and doubles each time. So we have 1 plus 2 plus 4 plus 8. So if you imagine this sequence continuing on indefinitely, each of these terms is going to be getting bigger than the previous one. Everything's doubling and doubling and doubling. And so what's going to end up happening here is if you add it together, you're going to find that this sequence basically keeps growing indefinitely. It goes to being infinitely large. I'm just going to write goes to infinity. And so it basically grows and grows and grows without anything restricting it. So the common ratio in this particular sequence, this is going to be true for any sequence or series where the common ratio is greater than 1. So if it's doubling, if it's tripling, that increase is always going to make the terms bigger and bigger and bigger. So this one, again, just like our arithmetic series, it diverges. So consider this next series. It's got the same terms as the previous one, but it goes 1 minus 2 plus 4 minus 8 plus 16. This one's actually alternating back and forth because here the common ratio is less than -1. And so what's happening here is actually we've got a negative number. It is making the magnitude of each term bigger, but then switching the sign. And so this one's a little bit tougher to wrap your head around conceptually because we're always sort of adding to the sum and then taking away and adding and then taking away. But the bottom line is this one's still going to diverge because over time what's going to happen is you're either consistently taking away more or adding more into the mix over time. And so this one is still going to diverge in some way as you keep going. The more terms you add, you're either going to find that the sum is getting to be much, much bigger towards the positives or much, much bigger towards the negatives. So that one actually diverges as well. There's no infinite sum possible for something like that. And so the really interesting case is actually if we start with 1 and perhaps apply a common ratio that is between -1 and 1. So let's say I pick the common ratio a half. My first term is 1. My next term would then be 1/2. The term after that would be 1/4, 1/8, and so on. So that's actually one where when it comes to finding the infinite sum, we could actually come up with a way of saying that actually approaches something. We would actually describe this as converging. So this sum converges, and it actually converges towards a number that's pretty easy to actually prove, even without using any sort of algebra. So let's picture it visually, and we'll start off with a square, or a rectangle. And so we're saying we're starting off with a full shape of that size. And then we're going to add in half of that shape on the next term. And then a quarter of that shape on the term after that. And then an eighth, which is half of this remaining piece. And then a 16th, which would be half of what's left. And 1/32nd and 1/64th. And if I keep splitting these pieces in half and adding them into the mix, what ends up happening is eventually I'm adding pieces that are so tiny, but still part of a whole, that really every term after this first one is basically just contributing to filling in this second shape. And so what this actually converges towards, this converges toward 2. And so as far as the infinite sum of that series, we would be able to say that is its limiting sum, that it converges towards a value of 2. So if you were asked what's the sum of this infinite series, 2 would be the valid answer, because you're going to keep adding in infinitely smaller slices, and eventually you will have filled in the entirety of those shapes. What this means is only a series with a common ratio between -1 and 1 will have a limiting sum, so that will converge towards some number. To find the sum of a converging infinite geometric series, we can actually just use this simple equation. The infinite sum is the first term divided by 1 minus r. This can actually be a fairly easy equation to develop. We kind of do it the same way we did for a finite series. Our infinite sum is just going to be u1 plus u1 times r plus u1 times r squared indefinitely. If I multiply both sides by r, what I'm going to get is the entirety of that first line, except for, again, term 1. It's really the only thing that's left over. So now I can take these two equations and subtract them. I'm going to do equation 2 minus equation 1. So I have r times the infinite sum minus the infinite sum on my left-hand side. And on the right-hand side, when I subtract everything, I'm going to actually be left with minus u1, because I'll take away everything here. I'll subtract this. So basically everything's eliminated except this piece, which ends up being subtracted from nothing. If I common factor now, I can factor out the infinite sum, and I get r minus 1. And if I divide both sides by r minus 1, I'm going to end up with this. Now, having a negative in the numerator maybe doesn't look as nice, so if I multiply top and bottom by negative 1, I get u1 over, and then it's going to flip the terms in the denominator. So 1 minus r. And that's my generalized formula for the sum of an infinite geometric series that happens to converge. So let's apply our new formula then to these two series that I've presented. The first series here is a converging series. Its common ratio is 1 over 3. The second series, though, I actually can't find the infinite sum for. It is a divergent series. The common ratio is 3 here instead. And so what that means is I can't find an infinite sum for the second one. It just gets infinitely large. But the first one, I can absolutely use my new formula here. So the infinite sum is u1 over 1 minus r. My first term is 3. My common ratio is 1/3, so I can pop that stuff in. So I end up with 3 divided by 2/3, which is 9 over 2. And so that would be the limiting sum of that series. It's going to eventually converge towards 9 over 2, or approximately 4 over 5. And that can be expressed as the limiting sum of that series. Whereas the second series doesn't have any sum, it diverges. It's just going to keep getting bigger and bigger and bigger. So that's the distinction then between a finite geometric series and an infinite geometric series. Finite geometric series you can find for any kind of scenario. An infinite geometric series, though, you have to remember to check, does the series converge first? If you know it converges, then you can find the sum of that infinite series.